Hey guys, we're back with the notes for 6.1. We're going to be on page 9 in your packet right now, and we are talking about systems of inequalities. We're going to do 5 examples today. Some of them are going to be linear, some of them are going to be absolute value, some of them are going to be quadratics, but the whole premise is the exact same thing. So we are trying to graph both of the shapes. We're going to shade, once we decide if it's solid or dashed line, shade on one of the sides of our graph, and then we are trying to find the solution. Just like when you graphed regular equations, the solution was where they crossed or where the lines crossed or where the two graphs crossed. When we do systems of inequalities, your solution set is going to be where the coloring intersects or where the double shaded regions are. I would highly encourage that if you have two colored pencils, not highlighters, not markers, not pens, but two colored pencils. That way if you mess up, you can erase. I would get in the habit of using that. Okay, so if you would, pause the screen for just a second, write down anything that you see, and then we're going to move on to problem 1. Perfect. All right, so it says the first step every single time is that we are going to rewrite the inequality to get the y by itself. Okay, so I always want to lead with the y. On this first graph, I don't like that the y is on the wrong side, so I'm going to flip it. I'm going to put the y first. Since I moved my y, I'm going to move my sign, and I'm going to say absolute value of x. All right, so let's graph my pink one first. We know that the absolute value of x starts at 0, and it goes rise 1, run 1, all the way out to the corner. So I'm going to kind of cheat and do that a little bit quickly. If you would just make sure very accurately that you are going up one box and over one box at a time. Okay. All right. I made an error in connecting it that quickly because here's the problem. My graph is a greater than, which means it does not have the solid line. So I'm actually going to edit mine and go back and do them with dashed lines. Okay, so if you've already drawn yours, you could go through and just erase little pieces of your line. That's an option. But we want to make sure that he is dashed. All right, remember we can always pick a point to decide where we are going to graph. Right now I'm deciding if it's on the inside or the outside. So if I pick a point, let's say I'm going to pick 0, 2, just to test it out. 0, 2 means my x is 0, my y is 2. Is 2 greater than the absolute value of 0? Yes, it is, which means that I want to include that point in my shading. I'm going to color inside here with my pink. Okay, so everything inside of here is going to be pink. Then we can switch to blue. Blue is linear. There is no absolute value on this one. There's no quadratic squared. So we're going to graph it like a straight line. We're going to begin on -2. My slope is just a 1, so rise 1, run 1. And on this graph, because it does have a greater than or equal to, I'm going to make him solid. So if you give me just a second, get all my points on here, we're going to connect it with a solid line. Okay. This graph is greater than, so we can pick any point we want to check it. So let's say I'm going to pick 0, 0 because it's on one side. Doesn't matter where it is for the pink. I only care about the blue. So if I plug in 0 is greater than or equal to 0 minus 2, this goes away. So 0 is greater than or equal to -2. Yes, since that point works, that is the side that I want to shade on. So I'm going to take my blue colors now, and I'm going to shade everything above this line. Make sure you shade even where it overlaps, even where it doesn't. You should be shading all the way to the edges. Okay? All right, so my solution set right now is only the places that are shaded in double color. So if I was going to kind of try to show that to you, this up here would be my solution set. Okay, and you don't have to put the lines over top of it. It was just me showing you. So if it was only pink, it would not be a solution. If it was only blue or white, it would not be a solution. Only where the purple is. Okay. All right, let's go ahead and try the next one. Anytime you need to pause the screen and get caught up, you may do that. Okay. So how do I determine if my solution's correct? Well, it has to be a solution for both equations. Okay, so that means that if there is no intersection of colors, that you would not have a solution. Let's take a look at this one. Remember that we would like to rewrite it to get the y by itself. So if I'm going to rewrite this first one, first thing I'm going to do is move the 2x to the other side. So 3y greater than 2x plus 6. If I do the same thing on the blue, moving the 2x to the other side, so I have 3y less than 2x minus 3, and now we still need to divide everything by 3. Okay, so if I divide everything by 3 on this top equation, I have 2/3 x plus 2. And on the bottom equation, divide everybody by 3, I have y is less than 2/3 x minus 1. All right, so we're going to graph both of these first. Both of them are a greater than or a less than, which means we're going to do dashed lines for everything. Let's start with the pink. I'm going to begin on 2, rise 2, run 3, and when I connect them, I'm going to use a dash line. Remember, if I'm going too fast, you are always welcome to pause and get caught up before you get confused. Okay. All right, if you're able to just know that greater than means above the line, that is absolutely fine. Hopefully you're getting that idea without having to plug everything in for linear. It does make it a little bit quicker. If you needed to check something, I could plug in a point. Let's do 3, 5. That way it would cancel. So I could say 5 is greater than 2/3 of 3 plus 2. That way my 3's cancel. 2 plus 2 is 4. 5 is greater than 4. Yes, that's why I can shade there. Okay. Get rid of that, just to show and justify it for you. All right, let's do the blue now. So for the blue, I would start at -1. It has the exact same slope, so rise 2, run 3. But this time when I connect it with a dotted line, hopefully you notice that we're going to go the other way. We are going to go less than, which means I want to be below the line. Well, that makes a problem, because if I shade this guy below his line, and I shaded the pink one above his line, then there is no purple. There is no mix. That means that these two graphs have no solution. It's not because the lines are parallel. If they were parallel and it looked like this, let me give you a quick example. If they were parallel and it looked like this, then they would have a solution because there is somewhere where they overlap. The problem is on this problem is on example 2, there is no overlap. Okay, so this graph has solutions. This one has no solution. Okay, if you need to pause the screen, go ahead and copy that down. We're going to move on to number 3. All right, number 3 is a little bit tricky. There are 3 graphs we are trying to get through. Okay. So we need to make sure we rewrite all of them to get the y equals, the y by itself. When we get all of them graphed, hopefully they make a perfect triangle. That's what it says anyways. And then we're going to describe what kind of triangle we have. Okay, so let's start by getting our equation set up. All right, first thing we're going to do is move the x to the other side. So -y less than or equal to a -x plus 7. Remember, when I move it, I change the sign. But on this one, remember that if you divide by a negative, you have to flip the sign. So we're going to say y is greater than or equal to a regular 1x, right? 2 negatives make a positive, minus 7. Let's talk about the blue one. Moving the 3x to the other side means I have -11y greater than or equal to a -3x minus 11. And then we do want to divide that one again, and because he's negative, we have to flip it. So y is less than or equal to a positive 3 over 11, x plus 1, and we have one more to hit. Last one, we're going to move that x to the other side, and on this one, I end up with a y by itself, so that means I get to be done. Y is greater than or equal to a -x minus 1. If you need to pause the screen for just a second and copy what you see, you may do that now. Otherwise, we're going to get started graphing with the pink one. All right, first thing I do right now is kind of scan, make sure everything on here has an equal to. So I'm going to do all solid lines when I graph this. Everything is linear, so I'm going to start with this one. Starting on -7, I'm going to rise 1, run 1. All right, all the way across my graph, connecting it with a solid line. And because it's greater than, I can shade it above. I'm not going to show you guys verifying that. Greater than a line means you are above that line. Okay, color my pink all the way through. If you need to pause it at any time and catch up with me, that's fine. We're going to go to blue. I'm going to graph this blue equation. So starting at 1, we are going to rise 3, run 11. So rise 1, 2, 3, over 11. So that's a big jog over to here, connecting it with a solid line. Let's see if I can get that as straight as possible. There we go. And because it is a less than, I want to shade him below that line. So everywhere below my line is a less than. All right, right now we do kind of have a triangle, but we want to make sure that we do our last equation to verify that kind of triangle. All right, last equation is the yellowy orange one. Starting on -1, we are going to go down 1, right 1, because my slope is a -1. All the way through, making sure that we connect it with a solid line. And then because it is a greater than, we are going to shade it above. So everywhere up here. All right, now there's lots of mixed areas, right? Lots of mixed areas. But the only place that has all 3 colors overlapping is this little zone right here. So this is the triangle that we're talking about. If you need to pause it for just a second to get caught up, go ahead and do that now. All right, the question is, what kind of triangle is it? So if I look at the first 3 options, so scalene, isosceles, and equilateral, this means all sides are different. This means that 2 are equal. Equilateral means that all 3 are the same length, okay? So if I look at that, it looks very clearly to me like those are different lengths, okay? The pink one is definitely shorter than the blue one, so we are going to call this a scalene triangle. Now, if you know much about triangles, you know that they're classified by the sides and by the angles. So if I want to classify it by the angles too, I'm going to have to look at those. Okay, so between the angles, we have obtuse, we have acute, and we have right. Okay, acute is probably the most normal one. That would mean if all the angles are less than 90 degrees. Obtuse would be if one angle is greater than 90 degrees. Right would be if one angle is equal to 90 degrees. Okay, so if I look at those, this angle is definitely small, less than 90 degrees. This angle is definitely small, less than 90 degrees. But this one's a little bit tricky, okay? I don't really know about this guy, so we could check it. Remember that we make a right angle or a 90 degrees if we have opposite reciprocal slopes. So if I take a positive 1/1, and that's this pink one, and I also have a negative 1/1, that's this orange one, they are opposites, right? One positive, one negative, but they're reciprocals too. 1/1 flipped is the same as 1/1. So that does make this a right angle. So we have scalene and we have a right triangle. Okay. If you need to pause that screen for just a second, write down anything you need. We do have 2 more problems. Perfect. Moving on to the bottom, we're going to talk about quadratics now. Quadratics mean we're back to parabolas. So I'm going to graph these using transformations. Okay, so that first one has a vertical stretch by 2. That does mean that it starts at 0, 0, but instead of following the regular 1 squared is 1, I'm going to double that and go by 2. Instead of saying 2 squared is 4, I'm going to double that and go up 8 on both sides. And that should give me enough to get my graph. Because it is an equal to, greater than or equal to, I'm going to go ahead and make it a solid line connected. And then if I could test a point to see which one would work, we want to know if it's shaded inside or outside. So I'm going to pick this point 0, 1 just to make my life easy. So the y is a 1. 2 times 0. That's saying 1 is greater than or equal to 0. Yes. That means I can go ahead right now and shade everywhere in here with my pink. And I'm going to try and make that a little bit smoother. Okay. All right, let's go to my blue one. So the blue one is going to be reflected over the x-axis, and it's also going to be up 1 space. So we're actually going to start where that black dot is, start on the 1. And when I flip it, I'm doing the 1 out 2 down 4. And remember, 3 squared is 9. So when I go out 3 boxes, I'm going down 9. Still a dashed line because I don't have an equal to on this one. And it is a less than. So let's pick a point that would be inside or outside. I'm going to use 0, 0 this time because that's right here, and that'll tell me if it's inside or outside. So if I plug in 0, 0, so 0 is less than a negative 0 squared plus 1. Zeros, remember, disappear. So 0 is less than 1. That is true. I can then shade everywhere inside that blue parabola. So my solution set, ooh, coloring got really layered there. Sorry, guys. My solution set then is everywhere that overlaps. And in this case, it's really just this little bitty area right in here, okay? That's all my solution set has. If you need to pause that, write down anything you need. We're going to do one more together. All right, so pink equation on this one is going to be an absolute value. Remember, this graph is going to the left 1 and then down 3. So left 1, down 3, it is a regular absolute value. So rise 1, run 1, and it is solid. So I'm going to connect that to all of the rise 1, run 1 corners. Ooh. There we go. Same thing going the other way. I want to hit all those corners. Let me see if I can get that. There we go. All right, it is a greater than, so we are going to check a solution, see which one would work. Let's check 0, 0 right here. So 0 is greater than or equal to 0 plus 1 minus 3. 0 is greater than or equal to the absolute value of 1, which is 1 minus 3. 0 is greater than or equal to negative 2. Yes. So because that works, I'm going to go ahead and take my pink, color everywhere in here where that point was. Last one is my blue equation. So for the blue one, basic linear, there's no squared or absolute value. We're going to start on 0, 0, rise 2, run 1. Make sure you go all the way across your graph. He is solid because he does have an equal to on him. And remember, a greater than means we want to be above all the points on this line. So I can take my blue, slide over this line, and we are going to shade everywhere greater. So I have lots of solutions set on this one. My solution set is anywhere up here in the shaded area. Wherever the colors are mixed, wherever that purple is, that's my solution set. Okay. If you need to pause, write down anything you need. Otherwise, we are done with the notes for 6.1.